position basis for a free particle and defined the states, so the basis states are continuous and are given by the kets that are just labeled by X. And the position operator capital X operates on these basis kets to give the position. Okay, so we covered that last time, and now we would also like to do the same for momentum. So we would so let's define the momentum basis. Given by the set of continuous states that are denoted by a P. So we have a little P in our ket, and there's a momentum operator P hat such that P hat, when it operates on a state with momentum P, just takes that, just brings out the P. So this is again just another, it's another eigenvalue equation, just like we have an eigenvalue equation for position. Okay, any questions so far? All right, now we also defined for a general state ket psi for a particle, we defined the position wave function psi of x was defined as x taking the inner product of a basis ket x with the ket psi. Okay. Now we had we have a completeness relation for the position eigenkets, or sorry, the position space kets. And we wrote that as the integral over dx of x is equal to 1. So that's just the completeness relation, says that you can expand everything, says that you can expand every ket in terms of the X basis. Okay, now, we also have a completeness relation for the momentum basis. And that says that we can integrate the operator P also, and that also gives us 1. Okay, so are there any questions about just the basic definitions that I've written down here? Okay, so let's go ahead and use some of these relationships now. So if I take let's call this let's let this ket operate, or sorry, let's let this operator here, or just 1, act on a general ket. Psi. So so psi is just equal to 1 times psi, but if I use this relationship here, then I can write this as an integral over dp like so, and we can define, just like we did for position, we can define this as psi of p. Okay, so that means we have, so if we take our relationship, then we have psi is equal to the integral over dp of psi of p, and we're integrating from minus infinity to infinity. Okay, now we can take the inner product now with one of the x states. So let's come in on the left with x. So we can write down that x psi then is the integral over dp minus infinity to infinity of psi of p xp. Okay, and this is psi of x on the left, so we have a relationship now between psi of x and psi of p, if we just know what this x p is. Okay, so this is an equation that gives the relationship between this is the space, position space representation, and this is momentum space. Okay, so we have two ways to think about a free particle, or in general, we'll be able to think about other particles in two different ways. We can think of them as the representation in X space, or we can think of them as a representation in the momentum space. Okay, and some people would put a tilde over the psi here, but it's a function of p, so you know it's a different function. Okay, so psi of p and psi of x are not the same function, just substituting extra p. They're different functions. So we have to figure out then what's the value of xp if we take the inner product between these two ket vectors. Okay, so we already know that we know one representation for p hat is minus I h bar times d by dx. So we can calculate, so let's calculate x p hat p. What's this equal to? Well, this is equal to two things. I mean, I can either use my relationship here to calculate, this p hat operator will just bring out a p. So I can write this as x, now p is just the momentum of the state, and that's just, I can bring that right out, p xp. That's one way to write it. And the other way to write it is in terms of this derivative operator. So we can write it as minus I h bar d by dx acting on p. Okay? So this expression, we can pull this d by dx out on the left-hand side and write this as minus I h bar d by dx acting on x and p. And so now we have two expressions. So we have minus I h bar d by dx xp, and this is equal to p xp. Okay. So what is this? I have a function, I take its derivative, I get the function back with a constant down there. So what's the solution?
That's the exponential again. You take its own derivative, the derivative itself gives you itself back as the exponential.
Right, it's an exponential function. So that means that I take the derivative of this thing, and it gives me I over h bar p times that same thing again. So this must be, so the solution is x p is equal to some constant a, e to the I over h bar px. Okay, it's an exponential. Okay, so what does that mean? That means that we can write psi of x is equal to the integral dp minus infinity to infinity of some constant a, e to the I over h bar xp times psi of p. Okay? So what's that? of transformation is that? Real common.
Is it a Fourier transform?
It's a Fourier transform, yeah. Okay, so let's do some, so they're related by Fourier transform, but let's work out this constant A. So to do that, let's just write down what a Fourier transform pair is. So let's use G of, I can use P, is equal to the integral of over dx, say, e to the I p x times f of x. Okay? I can do, this is just the same thing there, but if I want to write this, then f of x, the transform pair, the partner, is 1 over 2 pi times the integral over dp this time of e to the minus I px g of p. Okay, that's just the definition of a Fourier transform pair. And so what I want to derive now is, next is a integral form of the Dirac delta function, because we're going to need it. So what I'm going to do is plug this f back in here. Okay, so let's do that. So plug f of x into g of p. So if we do that, then I'll have g of p is equal to the integral over dx e to the I px and f of x. Now, when I write f of x as an integral over dp, I have to change the p here, because there's a p in here that goes with this p. It's not the same as this p here, because this is just another integral. I'm integrating this p out, it doesn't exist. So we have 1 over 2 pi integral over dp prime, and e to the minus I p prime x g of p prime. Okay? And the right-hand side should be equal to g of p. So let's collect our exponentials. So let's write this as the integral over dp prime. And then let's write g of p prime, and then I'm going to bring my integral over dx to the rear here, and put the 1 over 2 pi in front of it. And then I will collect my exponential, and this is e to the minus I x p prime minus p. Okay, so if this integral here over dp prime is to act on g of p prime and give g of p, then everything here in this integral must be equal to delta of p prime minus p. Okay, so that means we have an integral representation here. So we have 2 pi times delta p prime minus p is equal to the integral over dx of minus infinity to infinity e to the minus I ix p prime minus p. this is a very useful tool, especially if you're doing analysis with continuous functions. This is a great thing to use. Okay, so I just wanted to get to this relationship here. So now we want to let's find the constant of proportionality here, A. So now we will put the value of A in this equation. Okay, so how do we do that? Well, what do we know? We know that the integral over psi of x squared dx is equal to 1. So let's use that. So that means we have to take the conjugate of this. So we write psi star of x. That's the integral from minus infinity to infinity dp a star e to the I over h bar x p psi of p. Okay, and then we can so if we write down, so I'm going to write down the normalization condition, integral over dx of psi star of x, psi of x equals 1. So let's write it down. We'll have the integral over dx. Now, psi star of x, we just wrote that down as sorry, let's see here. If that's got a plus I, this has a minus I. We can write this as the integral over dp a star e to the minus I over h bar px times psi of p. Okay, that's one of those integrals, and then the other one is we have to do it over another integration variable. So if this is psi prime, this will be psi. This will be e to the plus I over h bar p prime x psi of p prime. Okay, and all of this has to equal 1. Okay, so we have, what am I going to do? I'm going to use my Dirac delta function. That means I want to collect my exponentials. The x is common, the p is not, so I want to be integrating over x here to get a Dirac delta function in p. So I can write this as dp prime psi of p prime. And then we'll have an integral over dx. I can bring out my a's, and this will be integral over dx of e to the I over h bar x p prime minus p, and this has to equal 1. So now, just by the definition of the Dirac delta function here, I can write this is just the same thing. This is just 2 pi h bar times the Dirac delta function p prime minus p. Okay. So what does that Dirac delta function do? Well, I'll integrate over one of these. Whoops, wait, let's see here. I have a star. I'm missing a star here. When I conjugated my psi, I have to conjugate this thing so that this psi of p is conjugated. Okay, so that means that we have the magnitude of a squared, the integral over dp. Now the integral over dp prime, I can use this Dirac delta function, and I'll just get, it'll turn this integral over p prime, it'll turn this into a p. So what we'll have is just 2 pi h bar times the integral psi star p, psi of p, and that has to equal 1. Okay, and so what do we do? If we look at our, let's see, I already erased it. Our normalization condition for psi, we're going to assume that this is also normalized, so that this should be equal to 1. So if that's the case, then A is 1 over the square root of 2 pi h bar. Okay, so then we have, if we go back to our equation double star here, so we have psi of x is 1 over the square root of 2 pi h bar integral over dp e to the I over h bar px psi of p, and psi of p is just the inverse. Okay, so for a free particle, free particle wave functions are Fourier transform pairs. For x and p. Okay, so what this means, so what does this mean physically? Let's just suppose that psi of x is a step function centered at the origin. So let's say it has a width L and a height then has to be 1 over L so that it's normalized. So then what is psi of p? Psi of p, so psi of x is 0 outside of L over 2 and minus L over 2. So psi of p is just is 1 over the square root pi h bar, the integral from minus L over two to L over two, it's just one, but the function is just L on the inside, so it's just L times e to the minus I over h bar px, integrating over dx. How do you integrate this?
It looks like what we did last time with our pi over a.
How do I just integrate just a simple exponential?
I mean,
Isn't it just itself?
It is, but
what was that?
what do I need? do?
Divided by the, divided by negative I over, h bar times p.
So I'm integrating over dx, right? This stuff is just,
That stuff is all constant up there. Yep.
so I need all of that stuff out front, right? So that means I need to divide by that stuff.
Yeah.
So that's L over the square root two pi h bar, and then we'll have, I just need to divide by this, so that's minus I p over h bar, right? Times e to the minus I over h px from minus L over two to L over two. So that's L over root two pi h bar. H bar over minus IP, and then we'll have here e to the, let's see here. I'll have,
Is one divided by negative I? Is that just I again?
it is. So it's minus I over h bar p L over two minus e to the plus I over h bar p L over two. Okay, now I'm gonna use this negative sign here and here. So I can flip these things around. So I'll have L h bar over the square root of two pi h bar. And I wanna add a two upstairs and a two downstairs. So I'll have e to the I over h bar p L over two minus e to the minus I over h bar p L over two divided by two I. All right, so what's this?
Is that a sine function?
Right, that's the sine function. So this is, well, let's see, I'll write this as, well, L h bar over the square root two pi h bar, let's see, I'll have two over p, and then I'll have sine of PL over two h bar. Did I put my L in the wrong place? Ah, the height's one over up, yeah, okay. This L is not up top. This is a one over L. Much better, I'm much happier then. Okay, does anybody recognize this function now? I'll write it as one over the square root of two pi h bar function is that?
Looks like the derivative of a cosine.
Hmm?
So that looks like the negative derivative of a cosine. No, never mind.
No?
No, it's not.
Is it a hyperbolic one?
No.
Oh,
Oh, okay.
so that's just the wave function in terms of position, momentum to the position.
All right, what does it look like? What does this function look like if we plot it? So, if I were to just plot sine x over x versus x, what does it look like?
It looks like a sine function that's like, is that a damping term? It's not really damping, but it's like when it decreases over time. Like the oscillation gets smaller over time.
Over space.
Over space, I mean, yeah.
Yeah, what's its value at 0?
Infinity.
Or undefined.
Yeah, it goes to infinity at 0, right? They're gonna have to go to infinity at 0.
No?
Oh, that's right, because sine of 0 is also 0.
What rule do you have to use?
L'Hopital's rule.
Right. The other way to look at it is, you know the expansion of sine x. What's the expansion of sine x? What's the first term in the expansion of sine x?
X.
Right.
That's a rule I haven't heard in a while.
Oh, L'Hopital's rule.
Yeah.
I remember it was my favorite. You could solve everything with that.
So as x goes to 0, sine x goes to x. So this thing goes to 1,
Oh.
right? It's a finite function. And then it oscillates and it dies, but it's got a width to it.
Right.
So this is p, the width here is, there's an L over 2h bar here. Okay, so if you plotted sine ax over ax, that you would have the width would depend on that a. Okay? So what happens? Let's see. I mean, what happens if L is very large?
Would that central hump just be wider?
I think the width of the bell part would get
Oh yeah.
it would get shallower, it would get smaller, so it would get like tighter, right? This is like, if we're going towards what I think we're going to.
It would have to be like shorter, right? Because you got that L in the
No, it's always 1
Oh, that's right. It's always 1. Because,
at
right,
0.
Right.
Okay.
I mean, there's a prefactor here, but
Right.
we're more interested in the width. I'm more interested in the width of this thing.
I'm saying the width would decrease on that one.
With larger L?
I think so.
Why?
Because I think we're approaching the Heisenberg uncertainty
Yeah.
principle with this.
So if we're looking at this function in terms of position, then if you like.
How would you figure it out if you didn't
Yeah.
know?
Okay.
With the larger L on the denominator, that would
Well, I mean, think about what happens if you just wanted to rescale the axis.
Right, yeah, if you make A larger, then doesn't that get narrower then?
If I make this little.
Yeah,
this
that
big.
A there, they make that larger, then it doesn't make it narrower.
Right.
So if you make L larger here, then it has to get narrower.
Right, if L is large, if it's spread out in position space,
Then it has to be narrower.
then it gets really narrow. It gets really narrow in momentum space. Okay, so this is the Heisenberg uncertainty principle. So if you, the more you know about the position, if this thing is really peaked, then this thing just spreads out and becomes a pure wave. Just becomes a wave of one frequency, actually. So it's just the width here will change, you know, the momentum space representation. So that's the origin of it. Now, this is a square, you know, function, and so and what we'll do later, we'll do this with Gaussians.
Is that what produces like a wave packet? It's basically like an envelope.
Well, we're gonna want to make a wave packet out of Gaussians, so I'm not going to use we won't use square waves. But this is just a way to, you know, this is a really common feature of, you know, Fourier transform pairs. So if you're localized in X, you know, if you're localized in one space, then you're not localized in the other, and vice versa. So that's really all there is to the Heisenberg uncertainty principle. It's no deeper than that. Okay, any other questions? Okay, so let's explore a little bit more about particles, but now let's have a potential. So we wrote this equation down before, but now I'm going to write it again. Where the Hamiltonian now is given, so we now have a potential V of x that might not be 0. Okay, so
Quick question.
yeah.
Why is that kinetic energy term negative?
Oh, it's sorry. Thank you. It's not until I put the. We can write it in terms of h bar though. Let's.
Okay.
I wanted to write it in terms of in terms of the derivative operator anyway. Yeah. Next. Okay, so we want to find solutions to this equation, but we also want to understand some general properties of it first. So let's see if we can understand some general properties of it. Okay, and so one of the things we would like to understand is, how does this thing relate to what we know from classical physics? How does quantum mechanics relate to classical physics? All right, that's not I mean, that's a really valid question because, once Schrödinger came up with the equation, it describes wave behavior we already talked about and things like that. And it's also a diffusive kind of equation. So how does it describe classical, behavior? And so if you want to understand, what is it that we want to understand from classical behavior? I mean, what do we know from classical physics? What's the first thing that you would think about if you were trying to compare quantum mechanics to classical physics?
In classical physics, like energy levels are like continuous, like there aren't really levels. Like the energy of a system can take on any value.
Sure. But what about just particle motion?
Oh yeah, in like classical mechanics, we treat things like they're like hard, rigid objects, not like they're waves spread out over space.
Sure. Okay.
There's certain, like, if you have a location of a particle and also its velocity and momentum, you don't have a distribution of its velocity and its momentum.
Okay, good. So how can we construct something similar to what we want? If all we know is the wave function, and we've talked about what it means. Remember that the probability of finding a particle in some interval, it depends on the square of the wave function between there, and just integrating over it. So if I want to describe the position of a particle, how do I do that? What would I calculate?
The expectation value
Of what?
of the expectation value of, I guess, where is the expectation value of the wave function, but in terms of x, right?
Yeah, okay, you got it essentially, right? So, yeah, that's what we want to do. So we can calculate, how about looking at something like the expectation value of x itself, right? That's
Okay, yeah.
But all we know is the wave function, so this is a calculation. This is the first moment, so this is psi star psi of x and t integrated over dx. Okay, that's right. If psi star psi is the probability distribution, then what we're calculating here is just the moment x in that distribution. Okay, so what we would want then, why don't we try to calculate something like the time derivative of x? So if this thing moves, I mean, here's the picture. We have, suppose we have this is psi squared at some t1, and then at some later time, we have psi squared at some t2, and the distribution has shifted. So, there's some, if this is the distribution, then there's some average x in there for that part of the distribution. And then when it moves, there's some average x here. So, this x moved from here to there. So we should be able to relate that to, for example, the momentum or something. So let's see if the formalism can do that. Okay, so what is then, okay, let's do, let me. To simplify things, let's rewrite the Schrödinger equation just to minimize the amount of writing that has to be done here. So, let's write partial derivatives as follows. I want to write the partial derivative with respect to t of x and t. I'm just going to write this as psi comma t. Okay. And then d by dx psi of x and t, I will just denote by 1 comma x. And then a second partial derivative with respect to x right is two x's. Okay, that'll save a lot of time in writing. And then let's rewrite the Schrödinger equation. So then, and I want to, let's put the IH bar over to the right-hand side. So I can write the Schrödinger equation as capital psi comma t is equal to, now I always get this wrong when I do this. Let's see here, let's see. I'm dividing by I, so I can bring it up top. I can write this as IH bar over 2m psi comma xx. And then that means that minus I over h bar v psi. Okay. And let's conjugate it, because we're going to need that. So the time derivative of the conjugate minus I h bar over 2m psi comma xx, and then plus I over h bar v psi. Okay? Oh, we need one more thing. Integration by parts. Does everybody remember how to do that?
Yeah. Oh, I hope they do.
It's been a while.
Yeah.
Okay, so if I have, so A and B now are some kind of things I can take a derivative of. So if I take the differential of AB, this will be B dA plus A dB, right? Everybody's in agreement with that?
Yeah.
And now I can integrate both sides. So if I integrate d AB, that's the integral of B dA plus the integral of A dB. But by the fundamental theorem of calculus, this is just, again, AB is equal to the integral b dA plus the integral a dB, and then everybody solves then for integral a dB. So the integral of a dB is equal to ab minus the integral of b dA, right? So that's
That's
that's the formula.
That's a lot less complex than I thought.
Well, it's a simpler explanation than the textbooks give.
Yeah.
No, I thought the textbooks did this.
I don't, so like, they do. I think the textbooks touch on this in calculus 2, but then they basically don't mention it again in calculus 3, and you don't really see that explicitly spelled out again until partial differential equations. So like, so if you didn't take PDE, then you just haven't seen it in like 3 years.
Oh, wait, no, partial.
Yeah,
Right,
I
for 2
take,
years.
ordinary ones.
Yeah.
So, yeah,
Okay.
Yeah, if you only take go up to ODE, then you saw this once like 2.5 years ago.
Yep.
All right, well, the only thing to remember is when you do this integration here, you have limits. So there's actually, a limit bar here. You have to evaluate this thing at the limits. So, let's look at, we want d by dt of this expression here. So let's see if we can calculate that. So we have d by dt of the expectation value of x then is the integral over dx. Now, we'll have psi star, we have to take the time derivative of that. I'll just use the chain rule, so, or not the chain rule, the product rule. So it's psi star t x psi plus psi star x psi comma t. Okay? I'm gonna try to keep things simple by not writing the limits or anything. Now, well, let's write them once. So this is minus infinity to infinity. And remember that we insisted that psi of x goes to 0 for x goes to plus or minus infinity. The wave function itself just vanishes because we're expecting the particle to be somewhere where we're doing our things, and it can't be finite as psi goes to infinity. Otherwise, it wouldn't satisfy the normalization condition also. Okay. So let's go ahead now and plug in for the Schrödinger equation. So this is integral over dx. Now, it just gets a little bit messy. So now we have psi star of t. So now I've got minus IH bar over 2m. Psi star comma xx. Oh, sorry, I have to, when I conjugate the Schrödinger equation, I've got to conjugate the wave function. So I've got minus IH bar over 2m psi star comma xx plus I over h bar v psi star. Okay. Oops, let's see here. I need multiple parentheses in here, so let's do this. Let's put x, and now I've just got the regular psi of t, which is IH bar over 2m psi comma xx minus I over h bar v psi. Okay? And then plus star, so this is minus. What am I doing? Wait, I put in Schrodinger's equation here. I did not want to do that, I just want psi. Much easier. Okay, plus, psi star times x times now psi of t, which is I over h bar, sorry, I h bar over 2m psi comma xx minus I over h bar v psi. Okay. Okay. So what can I cancel here?
Yeah, right, it looks like the complex conjugate of, was it the derivative of psi with respect to t is just a negative of psi, derivative of psi with respect to t, right? So you can just cancel out.
No, I need to cancel some terms in here.
Oh, right. Oh, those, yeah.
Right, I can cancel the potential terms, right? I've got a plus I over h bar v psi star x psi, and then here I just have a minus.
Okay. It's kind of a mouthful, because I was gonna say that, I was like, all
Okay,
of
so-
that junk?
So those terms cancel. All right, so what do we have left then? We've got the integral over dx. Now I'm gonna pull out an I, let's see, I'll pull out an I over h bar over 2m. Okay, dx. So then we'll have, let's pull out a minus. So it'll be a psi star comma xx x psi minus psi star x psi comma xx. Right, I think I got my minus that right there. Yeah. All right, so now, what, first of all, what do we expect? So you can't solve, I mean, it's really hard to solve a problem like this unless you kind of know what you're supposed to get. So what do you think we're supposed to get if we have, we're calculating dx by dt, we're calculating the expectation value, the derivative of the expectation value. So what should we get? What do you think we should get?
Yeah.
Right, which is, right, exactly, good, very good, momentum. Okay, so that means if we want this to look like the expectation value of momentum, then I gotta get, this x has to be gone. I just want psi star, I don't want anything down here either. I just want like psi star times the momentum operator times psi. Okay? So the question is how do you get there? And then, and now it's just, well, you know, what is the momentum operator? The momentum operator has one power of the derivative. So we somehow want to get just one power of the derivative left on the sides. So let's just integrate by parts. Let's integrate these guys by parts. And we'll use this. This will greatly simplify things because it will go to 0 at the endpoints.
So I think maybe that's supposed to be, the function goes to 0 as x goes to infinity.
Oh, yeah, 0. Yes. It cannot be finite.
I know.
Yeah, certainly not infinite. Okay. Alright, so let's see what's the first thing that we get here? So we'll have minus IH bar over 2M. Now, so I wanna integrate this thing by parts, what do I get? I wanna take the derivatives off of here and move them to the other side. Move them to the other things, I mean,
Right, so you get.
what integration by parts just allows you to do is to move derivatives from one operand to another, or one component to another. So let's just integrate it by parts once. What will that give us? Well, that means I've taken the derivative off of here, so this will be, I'll get psi star comma x psi evaluated at the endpoints. This is the AB term. Right? And then I have to put a minus sign and an integral. And now what do I have to, now I have dx, I've got psi star comma x. Now what do I have?
Psi comma x.
Well, I've got to take the derivative of both of these things together. So I'll have psi plus x psi comma x. Right?
I keep forgetting that x is a variable, not multiplication.
Okay, now this term here, because the function goes to 0 at infinity, just drops out. Okay, and now we've got to do this piece. This is a minus, and we'll put some brackets here. So this will be, I'm going to integrate this by parts, this psi double x. So I'll have psi star x psi comma x that is evaluated at the endpoints. So that goes to 0 minus now the integral over dx of taking the derivative of this. I'll have psi star comma x x plus psi star times psi comma x. Okay? All right. So now we have to hope for more cancellations. Do we get any more cancellations?
Well, when you do the thing times its kind, you're gonna get one, or, oh, let's just give you the expectation value of x and you just distribute through the comma x.
Hmm?
Okay.
Well, what do we want to be
I
gone?
like that it's just-
What term do we want gone anyway?
That psi comma x.
No, we don't want the x's in there.
Oh.
I don't want this term, and I don't want this term.
Yeah, and those do cancel.
And I've got a plus for this term
And a minus for
and a minus for that term, so thankfully these two cancel. Okay?
include.
All right, now what do I have? So this is minus IH bar over 2M, and now we've got, I've got minus the integral dx of psi star comma x psi, and then plus the integral dx of psi star psi comma x. Okay? We're getting close. What do I have to do now?
Do you have to do integration by parts again?
Yeah. Yeah. What do I want?
Because you're trying to get rid of that.
I want this. or I want something like that. Well, that means I need the derivative on the psi and not the psi star.
Yeah.
So I can just do one more integration by parts. This will just be psi star psi evaluated at the endpoints, which is 0. And then I'll get a plus integral over dx of psi star psi comma x plus this one here. Okay, so we're done. So what is this? I have just 2 of these, right? I have 2 of the same integral.
So you just add.
So I can cancel this 2 out here. And then so I've got 1 over m, and then I can bring in my minus IH bar. So I'll have dx psi star minus IH bar d by dx psi. Okay, so this is 1 over m times the expectation value of p hat. So we just showed that dx by, that m dx by dt is the expectation value of p.
And then you're dividing out the mass, so you get the velocity. Well, because like momentum is mass times velocity, right? So that's why it's 1 over m times the expectation value of p. 'Cause
Right.
then velocity.
I can also just bring it up to the other side and say n dx by dt is p. Okay, so so this is the way that you think about the wave function in terms of the classical physics that you know. It's in terms of expectation values. So when you write down the laws of physics and Newton's laws, there's actually this hidden expectation value for the math, the velocity and momentum and stuff like that. Okay, any questions? All right, well, see you back on Thursday. As long as we have